This video is going to be another Excel tutorial, and it will hopefully give you some appreciation for the work that van der Waals and the other people that made these equations of state have put in over the years. We're going to imagine that you do not know what the van der Waals constants A and B are for water, and we are going to fit them to data specifically for 300C. So we're going to determine the van der Waals constants by doing curve fitting. I want to point out that you wouldn't necessarily do this, especially because we do have values. You could look up online what the van der Waals constants are, A and B for water. But I want to make this into a video because it's part of a broader use of Excel. So you can use Excel to do curve fitting in other type of contexts as well, not just in thermodynamics. This is just one really interesting application of it. So the first thing that we're going to need to determine what the constants are some experimental data. So you need to go into the STEAM tables in your Sandler textbook and get some data points for 300C. I'm going to only select a few data points. I'm not going to do them all because that would be pretty exhaustive. All I want to do is just make the point of how you would use Excel to curve fit. So I'm going to pause the video and jump ahead to do that. Okay, so here is the data that I selected. As I said, I didn't do all the values that I have in the back of the Sandler textbook. I just chose a couple of pressures. I got a good range, so I'm going from 0.1 megapascals, about 1 atmosphere, all the way up to 30 megapascals, and I have the corresponding V hats specifically for the 300 degrees C isotherm. So I want to plot this data just to get a sense of what it looks like, but before I do that, I want to convert my V hat into V underbar. So I need to convert this specific volume to a molar volume. So I'm going to make a new column, call that V underbar, and that will be in meters cubed per mole. And in order to do this calculation, I need to convert. So there are 18 kilograms per kilomole. So I need to say, to do this conversion, I need to multiply by 18 and divide by 1,000 because a kilomole is 1,000 moles. And now this will give me my molar volume in meters cubed per mole. And I can now go ahead and plot this data. So I'm going to highlight my X and Y, insert, and it is going to be a scatter plot because it is experimental data. And why do I have two data series? I only want one data series, and I want my volume values on my x-axis. So is that what I have? No, I have it flip-flopped. So I need to say my x values are volume, my y values are pressure. Okay, now that looks good. So it looks kind of similar to the pressure versus volume plots that we saw in the last video. I can tell just barely if I zoom in a little bit, maybe I'll have to adjust the axis, but there seems to be clearly two different regions of this plot. So these three data points that are corresponding to the highest pressures, so 10, 15, 30 megapascals, seems to be fit by almost a straight vertical line. And then the other pressures have this kind of 1 over X type of fit to them. So the saturation pressure is probably somewhere between 5 and 10 megapascals just by looking at the plot. And by actually looking in the STEAM tables, the saturation pressure is 8.5 megapascals around. So that makes sense. So this is the jump between the superheated vapor state and the subcooled liquid state. So again, I want to find the values of A and B that closely represent all of these data points in this plot. So in order to do that, I'm going to make a new column, and I'm going to call it pressure, megapascals, and calculated. So this is going to be like the fit of my data. So the idea here is to guess values for A and B, and I'll use Solver to figure out exactly what they should be in a second. And I'm going to calculate the value of P given a value of molar volume, which I already have from the data, and values for A and B. So I'm going to need values for A and B at the beginning. And I need some initial guesses. So at this point, I have no idea what A and B should be. I could look it up, but I'm going to pretend that I am doing this for the first time on a compound that I have absolutely no idea, and I'm going to just make a guess. So for A, I don't know, 0.05, and for B, 0.0 0.01. That's not a bad guess because I know that the molar volume of water is 1,000 kilograms per meter cubed. Actually, B has got to be a little bit lower than that. So I'm going to make it 0.0001. And again, these are just initial guesses. These are probably going to be way off, but you just need to put something there, and I'll show you why in a moment. I'm also going to need my R, my gas constant, and my temperature. And my temperature is going to be 300 C plus 273 because whenever I'm dealing with the gas constant R, it's always in absolute units of temperature, never in Celsius or Fahrenheit. So my value of R for these numbers, so let's see, I'm going to need megapascals, Kelvin, moles, and meters cubed. So I know it's 8.314, but that's in pascals. So to convert to megapascals, I need to multiply by 10 to the minus 6. And the units here are megapascals, meters cubed per mole per Kelvin. Units there are Kelvin. Units of A and B will be consistent with what we have. So now at this point, I can calculate what my pressure is going to be based on these values. So I'm going to say equals and then use the van der Waals equation to fit this data. So I've got equals R, and I want R to stay constant, so I'm going to hit F4 to $ it, times T divided by V minus B. And I want B to stay constant, so I'm going to $ that one, minus constant A, which is $ divided by V squared. Okay, and I'm going to drag this all the way down, and I want to plot my data, superimpose it to see what it looks like. So I want to add a data series. My second data series is going to be V, is still the x-axis, but now this time my y is going to be the pressures that I calculated. And as I suspected, it's way off because I just guessed what the values of A and B are. So how do I go about getting a better estimate for what the values of A and B should be? Well, I need some measure of how well the data fits. So oftentimes in engineering, what we do is we calculate how far off. So just the difference between the actual pressure and the pressure that we calculated is going to be something that's good to calculate. So P minus P calc. And in this cell, I'm going to say it's equals the actual value of pressure from experimental data minus what we calculated. This is going to give us our difference. And hopefully the data or the values that we choose should minimize these differences. However, I'm going to want to square these because sometimes the difference may be positive, sometimes it may be negative. So I'm just simply going to say P minus P calc square. And in the formula as well, I'm going to do the same thing where I square these residuals, as they're called in statistics. All right, so this represents how close I am. And I've got some huge numbers here signifying that I'm way off. Times 10 to the 15 is huge. And in this cell, I'm going to call this the sum of squared errors, the SSE, and I'm going to say that is equal to simply the sum of all these. Now, the best fit values of A and B is going to minimize the value that's in this cell. I want to minimize the sum of squared errors because that is going to represent values that are generally good. So now in order to do that, I could, again, guess and check. So I could guess values of A, but then even if I find the value of A that minimizes this, I then have to find the value of B corresponding to that A. So I've got two values that I have to adjust in order to minimize the sum of squared errors. So clearly I'm going to need some help from the computer at this point. So I'm going to go to my solver, so data solver, and I need to set an objective. I've said in words that my objective is to minimize the sum of squared errors. So my objective cell is going to be the cell that has my sum of squared errors, and I want to minimize it. All right, so this is a cool thing that's in Solver that is not in GoalSeek. You cannot use minimum in GoalSeek. You can only use GoalSeek to set an exact value. You also, I don't think in GoalSeek you can change multiple cells, but I can't remember if that's true. In Solver, you definitely can. So this is absolutely a Solver problem. I then want to make unconstrained variables non-negative. I want to uncheck that. I want my unconstrained variables to be whatever. and I'll hit solve. And okay, so I think orange is my fit. And actually to fix that, I want to make my fit line a solid line. That's typically what you do in your data fitting. Your data points are individualized discrete markers, and your fit line is a smooth line with no data markers. So that actually looks pretty decent. You may think, why don't I have that distinctive shape of the cubic equation of state where there should be a maximum here and then it should shoot all the way down and be a minimum. So see if you could think about why necessarily that is, why you don't see that shape. And it's because I'm plotting only discrete points. So let's say instead of plotting this fit, let's say I make a new column, and I'm going to say this is just simply for my fit data. And let me make this a little bit bigger. All right, so I'm going to plot now V underbar as a function, or plot pressure as a function of V underbar for what I calculated, MPA calc. All right, so instead of just these values of V underbar for which I have data, I want to plot it in a way that's much more smooth and it doesn't quite look like that. So I'm going to start super, super low, 0, 0, 0, 0, 1, maybe. Yeah, I do want to start that low. And then I want to plot more data points than what I just have here and hopefully try and capture the whole shape of the curve. So I want to say G15 plus 0.0001, and I want to copy that down for a while to get some good behavior. And Microsoft Excel it's super cheap to do more calculations. It's not going to slow down my computer at all. So I'm going to go all the way up until 0.01, and then from this point forward, I'm going to add 0.001. So get a better range of this data. And I don't know how far I want to go. That'll probably be good. I want to then do my calculation again. So I'm going to take equals, and it should be the same formula as here. So actually, instead of that, I'm going to say copy, this one, copy and paste the formula. So under special pasting options, I have the option to paste the formula. And let's see. Okay, that is going to copy the exact thing. So it is going to keep the absolute cell references the same, and it is going to make my relative cell reference equal to V underbar, which is exactly what I want. So that's a little bit of a shortcut that you can use. And I'm going to copy this all the way down. And now, instead of plotting this, I want to plot the more values that I made. And I need to drag these all the way down because I know I want to tell it to fit more of my data. Come on, there we go. Okay, let's see what this looks like. Oh, that doesn't look very good at all. What is going on here? Oh, I know. I think it's just my axes range. So I want to clean this up a little bit. I don't want to go from 1 million to -5 million. The range of my megapascals is only 0.1 to 30. So I want to go, let's say 40 is a good maximum to shoot for. And the minimum, let's say, is just simply 0. And okay, now here you see that the fit is a lot better. And I'm going to zoom in a little bit so you can see a little bit better how that behavior looks. So I'm going to set the maximum to 0.1. And let's go a little bit further than that. Let's say 0.01. All right, so here is that distinctive cubic equation of state form. And that's what we wanted to see. All right, so this is, again, how you would use Excel to do curve fitting and find the values of the van der Waals constants. An interesting exercise here would be to compare these values to what you'd get online. So I'm actually going to show you that as well in this video. All right, so I went to Wikipedia, and I want to be clear that Wikipedia is not the source that I would prefer to get my data from. There's many different sources that you could go to get these constants. like Perry's Handbook, the NIST data site could possibly have these. I'm just using Wikipedia to illustrate what how you would compare like to actual published values. And on first glance, the values from Wikipedia may seem like they're way off. So my value of A that I calculated was minus about 5 times 10 to the minus 8. Wikipedia says 5.5. So the moral of this story is that you have to pay attention to your units always. The Wikipedia units are in liter squared times bar divided by mole squared. What are my units of A from the plot that I did? Well, they should be, let's see, I want units of pressure back in megapascals and divided by my units of molar volume. So my molar volume is in meters cubed per mole, and my pressure is in megapascals. So my units here are in meters to the 6th times megapascals divided by mole squared. So there's going to be some unit conversions I have to do. And my B constant is going to be meters cubed per mole instead of liters per mole. All right, so to convert these and compare them, I'm going to take liters, and there are 1,000 liters per meter. So I'm going to say this is equals this one divided by 1,000, right? Because 1,000 liters per meter cubed. And that is going to get me a comparison between my B's. So Wikipedia tells me that my value of B is actually a little bit lower. And my value of A, so to convert this one, I need, what is it? I need to convert megapascals to bar to megapascals and liters squared to cubic meters. So I'm going to need to multiply this by times 0.1. So that's bar to megapascal. And then liters squared to cubic meters is going to somewhat cancel with the mole calculation. Hold on, I'm getting confused with my notes. Okay, I think I got it. So I have to multiply this one by 0.1 because there are 0.1 megapascals per bar, and then divide it by 1,000 squared because there are 1,000 squared liters squared per 1 meter cubed squared. All right, so my value of A that I get is a whole order of magnitude off, it looks like. So what gives here? What's the differences between the published values and what I got? Well, the first thing to realize is that I did not take all the data that I possibly could. So there's a small chance that just by taking more data points that I would get a better fit. Actually, that's almost a certainty that usually the more data points that you take, the more accurate your fit will be because you have more stuff to go on. The second thing is that I determine the best fits for one specific temperature. And importantly, values of A and B for the van der Waals equation of state are not functions of temperature. That's one of the reasons why it's not as accurate as some of the other equations of state. But because I'm doing this for one specific temperature, it's not going to be necessarily the case that these values are going to work the best for all temperatures. The third point I want to make is that simply the van der Waals equation of state is just not as accurate as some of the other equations of state. It's one of the earliest and a vast improvement over the ideal gas law equation of state because you can accurately model the liquid. These are the liquid ones, by the way. The ones that are in a straight line are for liquids, and these curved ones are for vapors. All right, that is the conclusion of this video. Oh, before I actually go, I want to mention one more thing that you can do. I want to actually go back to my OneNote notebook. Remember, I derived this last time. I showed you how to calculate the van der Waals constants. So you could also say that, get the value of A and B this way. So you could look up the critical temperature and pressure for water, and you could compare that to both what literature tells us and what your curve fit tells us. And that's another way that you can double check your answer. But I guess the broader point here is that you have to never take something at face value. Don't just take a value of A that you see from a textbook and slap it in. You have to really think about whether or not it makes sense in the context of the problem. And oftentimes plotting the data can give you a good visual representation of how good your data fit is. All right, that's all for this video.